All right. Hello, all. I wanted to go ahead and make a quick video to help with the um, the exponent rules. So this is going to be for the Objective 11 warm-up assignment in ALEKS. I'm decided to make this assignment extra credit for you. So this will kind of refamiliarizing yourself with the exponent rules will make homeworks 11 and 12 a little bit easier for you. I hope that you do it. It's extra credit. It should help you. So let's go through this a little bit and hopefully it will help you. So our basic exponent rules here, if you are multiplying two exponential expressions with the same base, nope, this one, like this one here, then if you're multiplying two things with the same base, what you want to do is add those exponents. So x to the a times x to the b is x to the a plus b. You'll add the exponents. Similarly, if you are dividing two expressions with the same base, you will subtract those exponents. So x to the a divided by x to the b will be equal to x to the a minus b. If you have powers, two powers, like this one down here, x to the a, that whole thing to the b power, you will multiply your exponents. This will be equivalent to x to the a times b power. If you have a quantity to a power, as long as what's inside your quantity is multiplication, like this one here, or division, like this here. Sorry, there shouldn't be an equal sign in here. But if you have a quantity with multiplication or division inside, and that whole quantity to an exponent, you can distribute that exponent to everything inside. Again, you can only do this when it's strictly multiplication and division only inside the expression. So when you do that, x to the a to the c power here will be x to the a times c power, because again, coming back here, powers, two powers, we multiply them. So the x to the a to the c will be x to the a times c, and we're going to multiply that by y to the b times c. You'll apply this exponent to everything inside. Similarly, if you have division, we can apply this exponent c to everything inside. This will be x to the a times c all over y to the b times c. Now, what if you have addition inside a quantity like this one? Can I distribute that exponent c to everything inside? The answer is no. You can only distribute an exponent when it's multiplication or division inside the quantity. This addition is going to ruin this for us, and there's no simplification that we can do for this problem. It's important to understand when you can simplify and when you can't. That's an important distinction, and I want you to be familiar with that. So generally, addition and subtraction are going to ruin our algebra parties. So if there's addition inside, you cannot simplify that. Okay, next is anything to the 0 power is 1. This is just kind of an understood rule. If you have any questions about why that is, I'm happy to explain it to you. Basically, anything to the 0 power is kind of our multiplicative base. It's where we start multiplying, and 1 is our multiplicative identity, so that's where we start. I can give you additional ways to think about this. If that's confusing for you, let me know, and I'd be happy to go through that with you on an individual basis. For our purposes in this class, anything to the 0 power is going to be 1. So 5 to the 0 power is 1. How about 397 to the 0 power? Still 1. What if I have 3a to the 4th, b to the 7th, c, I don't know, to the 26th, all to the 0 power? Still 1. Doesn't matter what's to the 0 power, it's 1. The next exponent rule is negative exponents. So if I have something like 5 to the -1 power, negative exponents are going to give us reciprocals. So it's going to move us across the division bar. So 5 to the -1, I'm going to think about that as 5 to the -1 over 1. This negative exponent says, you can't stay here. I don't like negative exponents. You cannot be here. And it's going to say 5 to the -1, you need to move. So what it's going to do is it's going to jump over that division bar and it's going to come down here to the bottom. When it does that, the negative disappears from our exponent. So we go from 5 to the -1 on top. That negative exponent says, get out of here. And when it crosses the division bar, we end up with 5 to the positive first power on the bottom. Once this moves, there's an understood 1 up here. And so 5 to the -1 is 1/5. What if we have 5 to the -3rd power? Well, again, that's 5 to the -3rd over 1. That negative exponent says, you can't stay here. I need you to move. So it's going to cross the division bar and come down here. When it does, that exponent of 3 will go with it, but the negative disappears as soon as it crosses the division bar. So 5 to the -3rd power ends up being 1 over 5 to the 3rd. If you like, you can do the 5 to the 3rd power, and that would be 1 over 125. Now, what if you have things with positive and negative exponents in them? Such as, how about 3x to the -2, y to the 4th. Anything with a negative exponent will move. Anything with a positive exponent is going to stay. This -2, that exponent that's negative, that applies only to the x. Everything else here has a positive exponent. The exponent here on the 3 is 1. And so the 3 of the first will stay. The negative exponent on the x will say, buddy, you need to get out of here. And so it's going to cross the division bar and go down here. When it does, that negative will disappear from the exponent, and we'll get x to the +2 on the bottom. The y to the 4th, that has a positive exponent, so it will stay. So the 3 stays up here, the y to the 4th stays up here, and just that x to the -2 moves to the bottom. And then one final example, what if I have a negative exponent on the bottom? So what if I have 1 over 5 to the -3rd? Wherever on the division bar that negative exponent is, the negative exponent says, you can't be here, you need to go. And so this is going to jump across the division bar. When it does, it's going to come to the top now. So I'm going to have the 5 coming up here. The exponent of 3 goes with it, but the negative disappears as soon as we cross the division bar. So 1 over 5 to the -3 becomes 5 to the +3rd power on top. And again, you can simplify that if you want to 125. So basically, negative exponents give us reciprocals. It moves across the division bar. That's what negative exponents do for us. So let's practice with some exponent rules. The biggest thing that we're kind of going to work through in these first few examples is, what does the exponent apply to? It's really important to understand what exponents apply to and what they don't apply to. Unless there are parentheses, it's understood that the exponent will apply only to the base right in front of it and nothing else. So let's start here with number 1. 2 to the 2nd power, that's going to be 2 times itself. So 2 times 2 is 4. All right, how about number 2? Negative 2 to the second power. There's no parentheses here, so this exponent of 2 applies only to the base of 2. It does not apply to that negative. There's no parentheses, so it doesn't apply to anything except that base right in front of it. So since there's no parentheses, this means -1 times 2 to the second power. So that means -1 times 4, which is -4. Now that you'll notice was different than number 3 here. So now this number 3 has parentheses here. That means that exponent of 2 will apply to both the 2 and the negative in front of it. That means this is going to be -2 and multiplied by itself 2 times, -2 times -2. Those negatives will now cancel out and we are going to get a +4. The difference between number 2 and number 3 here was the parentheses. Those are hugely important. Without parentheses, the exponent applies only to the base right in front of it and nothing else. Okay, number 4, 2 to the 0 power. Well, anything to the 0 power is 1, so 2 to the 0 power is 1. How about number 5? -3x squared. There's no parentheses here, so what that means is this exponent of 2 applies only to the x and nothing else. So this problem is saying -3 times x squared. And there's actually no simplification or exponent rules that we can apply to this. There's no simplification that can happen here. This is going to stay -3x squared. Not everything is going to simplify. It's important to understand when we can apply the exponent rules to simplify and when there's just nothing we can do. This is a case where there's nothing to do. So it's going to look exactly the same as it did before. Nothing to do here. Now, number 6 is a little different than number 5 because now we have parentheses. Now that 2, that exponent of 2, is also going to apply to the -3. This one says this is going to be -3x times itself. So now we're going to get -3 times -3. That's going to give us a +9. And x times x will give us an x squared. So once we have parentheses here, the quantity -3x squared is going to give us +9x squared. All right, so how about number 7? -3x, that quantity to the -2. This is all over 1. And so that exponent of -2 says, you can't be here, you need to cross the division bar. So we're going to go ahead and have that -3x move across the division bar. When it does that, the exponent of 2 goes with it, but the negative disappears as soon as we cross the division bar. So we're going to have a 1 left up here. That -3x, that quantity squared, moves to the bottom. Now we can evaluate this. This is going to be -3x times -3x here on the bottom, and that's going to be 1 over +9x squared, all in the denominator. Okay, number 8. This looks like a lot like number 7, but we have this negative hanging out in front here. So what that means is that's going to be a -1 times that quantity -3x to the -2 power. The exponent of -2 here says you can't be here, you need to cross the division bar. And so this -3x is going to move to the bottom. When it does, it will have a positive exponent of 2 down here. And the -1 that was up here does not have a negative exponent on it. It's just kind of here hanging out. It's going to stay exactly where it is up here on top. And so now we can evaluate this. We've got -1 over -3x times -3x, and we just did that. That's going to be +9x squared down here. So you will only move the things with negative exponents on them. Anything without the negative exponent here, like that -1, is going to stay put. All right, let's try a few more. Number 9, I've got a whole quantity to the 0 power. That whole thing to the 0 power is going to be 1. If anything to the 0 power is 1, I don't care how complicated it is. How about number 10 here? What we have is 5x squared y to the 0. Now this exponent of 0 only applies to the y in front of it, that base of y. It doesn't apply to anything else. So the only thing that 0 exponent is going to turn into a 1 is the y. And so the 5x squared is being multiplied by that y to the 0. And so we're going to end up with 5x squared times 1, or just 5x squared, because that exponent of 0 applies only to the y. How about number 11? What does that 0 apply to? Does it apply to the 5, or does it apply to -5, the whole thing? There's no parentheses here, so that means that the 0 applies only to the 5, and this really means -1 times 5 to the 0. Because there's no parentheses, this is how this is going to work. And so -1 times 5 to the 0 is -1 times 1, which is -1. All right, number 12. I've got 3 times x to the -4, y to the 3rd. I have a negative exponent in here, but I also have some positive ones as well. So we are going to put this over 1, and we're going to play a little game of should I stay or should I go? So we've got 3 being multiplied by x to the -4th, being multiplied by y to the 3rd. We're going to take each factor individually. So 3 here, is that going to stay or is it going to go? To decide that, we're going to look at the exponent. 3 has an exponent of +1. Because that exponent's positive, the 3 is going to stay right where it is, up on here on top. Now, x to the -4th, is that going to stay or is it going to go? The exponent of -4 says, you got to go, get out of here. It's going to cross the division bar, and it's going to come down here and have a positive exponent on the bottom. So that x to the -4th becomes an x to the +4th in the denominator. And then finally, the last factor here, this y to the 3rd power, should it stay or should it go? The positive exponent says it should stay, so the y to the 3rd is going to stay up here on top with the 3. So overall, I have 3y to the 3rd all over x to the 4th. Okay, how about number 13 here? I've got a lot going on. I've got a big quantity to the -2. I've got negative exponents inside my quantity. I've got negative exponents on the outside that apply to the whole quantity. There's a few different ways to think about this, and each person's brain might do things differently. If you want to do things in a different order than my brain does, that's totally fine. We should still get the same answer in the end. So since I have a whole quantity to an exponent, this exponent of -2 is going to apply to the 3, the x to the -4th, and the y to the 3rd. I can distribute that exponent to each piece. I'm going to do that before I start to play should I stay or should I go. I think my brain works a little bit better that way. If you want to move this whole quantity to the denominator to get rid of that -2 exponent on the outside, you can do that first. But my brain likes to distribute that -2 right off the bat, and then I'll play should I stay or should I go. So I'm going to distribute this exponent of -2 to each piece here. So 3 to the -2 power is 3 to the -2. X to the -4th to the -2 power, I'm going to multiply those exponents. That's going to become x to the 8th power. And then y to the 3rd power to the -2 power. Again, I'm going to multiply those exponents and get y to the -6th. So now that I've distributed this exponent of -2 to everything, now I can play should I stay or should I go. I'm going to put that all over 1. Here we go. 3 to the -2. Stay or go? The negative exponent says you gotta go. So we're going to move that to the denominator. When we cross the division bar, the exponent becomes positive. X to the 8th. Should it stay or should it go? The positive exponent says stay. And y to the -6th. Stay or go? Negative exponent says get out of here. It's going to move to the bottom. And then finally, if I wanted to, 3 to the 2nd power, I know what that is. So I can simplify this to x to the 8th over 9 times y to the 6th. And that will be our final simplified version. Number 14 here is going to work much the same way. Again, this is a choose your own adventure. You can do things in a different order. If your brain likes it in a different order, feel free to do that. The way that my brain works is I want to distribute this -2 and just kind of get rid of it and apply it to anything that I can. And then I'll play should I stay or should I go to the whole thing. So the -2 only applies to the quantities here. So the 3 is still going to hang out here, no problem. And the 2 doesn't apply to it. So it's just still going to be 3. X to the -4th to the -2 power. I'm going to multiply those exponents and get x to the 8th. And then y to the 3rd to the -2. I'm going to multiply those exponents again and get y to the -6th. And now that I have distributed that -2 power to everything in the quantity, I'm going to put this over 1 and play should I stay or should I go? The number 3, positive exponent says stay. X to the 8th, positive exponent says stay. Y to the -6th, negative exponent says go. So overall, I have 3 times x to the 8th all over y to the 6th. Okay, number 15 here. Again, there's a few different ways that you can start to tackle this. Again, I like to distribute this exponent first. I only have multiplication in here inside this quantity, so I can in fact do that. So I'm going to distribute that to everything inside that quantity, and I'm going to get 3x squared out here times x to the -4th to the 3rd. Multiply those exponents. That's going to be x to the -12th. And y to the 3rd power is y to the 3rd power. I've got 2 things being multiplied here with the same base, so I can combine these and simplify a little bit. So I'm going to get 3 times x to the 2nd power times x to the -12th power. If I'm multiplying 2 things with the same base, I'm going to add those exponents. So I'm going to get x to the 2 plus -12. That's going to give me -10th power. And then I've got this y to the 3rd here. Because I have a negative exponent, I'm going to play should I stay or should I go? The 3 and the y to the 3rd power will stay. That x to the -10th will go to the bottom. And we are at 3y to the 3rd over x to the 10th. All right, number 16. There looks like a lot of things going on here. There's a lot of different things that we can combine and move around. But again, because I have a quantity to a power, I'm programmed to do order of operations. And order of operations says I'm going to do parentheses and exponents first. So I really, really want to do this first. That's how I'm programmed. That's how my brain likes it. So that's where I'm going to start. Because I have multiplication in here and only multiplication, I can go ahead and apply this -1 power to each thing in that parentheses. So I'm going to kind of copy everything else down here. And now I can apply that -1 exponent to everything in the parentheses. x to the fourth power to the negative 1, I'm going to multiply those exponents and get x to the negative fourth. Y to the negative 2 to the negative 1 power, multiply those exponents to get y to the positive second power out. Okay, I have some negative exponents here, so I'm going to play should I stay or should I go. The 2 is going to stay. The x to the negative 2 is going to go, so I'm going to put that down here on the bottom. Y to the third, that's going to stay. Negative 3, that's going to stay. X to the negative fourth, that's going to go. And y to the second power, that's going to stay. So now everything has a positive exponent, but I've got x's on top and bottom and y's on top and bottom. So I can go ahead and simplify these guys. 2 over negative 3, that doesn't simplify, so I'm just going to leave that as 2 over negative 3. Y to the third divided by y squared. I can subtract those exponents, so y to the third divided by y squared is y to the 3 minus 2 is 1. So I'm going to get y to the first power on top. Or you can think about it like canceling like we did. Y to the third means you've got y times y times y, 3 y's on top. And y squared on the bottom means you've got 2 y's on the bottom. 2 y's from the bottom will cancel 2 y's on top, and you'll have 1 y left on top. You can think about it either way. And then now the x's, I've got x's on top and bottom. I've got 4 x's on top, 2 x's on the bottom. So when we cancel or subtract those exponents, we are going to get x to the second power up here on the top. And I'm simplified. All right, hopefully that all makes sense. You'll have to practice those, and if you're a little rusty on these, just keep practicing. Be careful with your exponents. Go slow, take your time, and play should I stay or should I go. The last thing that we want to go through here is fractional exponent rules. So what if I have fractions as exponents? For instance, what if I have 5 to the 1/2 power? Well, fractional exponents are actually roots or radicals. Those are two words for the same thing. And so this is going to create a second root because this number on the bottom here is 2. So 5 to the 1/2 power is a second root. And so this is going to create the second root of 5. Now, second roots, these are square roots. So we're used to seeing it without this index of 2 being written. If there's no index on the radical, it's understood to be a 2 and a square root. If the index is anything other than 2, it must be written in. So for instance, if I have 5 to the 1/3, this is going to create a cube root or a third root. The number on the bottom is going to match the index of the radical that it creates. So 5 to the 1/3 is going to be the cube root of 5. And then what if I have numbers on top and the bottom? For instance, what if I have 5 to the 2/3? Well, the number on the bottom is still going to create the index of the radical. So this is going to be a cube root. The 2 on top is actually going to go with the 5 as an exponent inside. So this is going to be the cube root of 5 squared. We can rewrite that as the cube root of 25. So the number on the bottom creates the index of the radical, the thing that goes in here. The thing on top goes with the base to the inside as an exponent. To write this pattern in general form, I can say that x to the m over n power, we can write this as the nth root of x to the m power. Kind of a fun fact, we're going to write it in this form more often, but we can actually also put this exponent of m on the outside of the radical if we want. So this is equivalent to the nth root of x, that whole thing to the m power. We can also write it like this. These two expressions here are equivalent. More often than not, you're going to put that exponent inside. Just know that m can come to the outside like this if we need it to. We probably won't use that one quite as often, but it is equivalent, so that is something that we can do, a way that we can write this. So let's practice using some fractional exponents and roots. So the sixth root of x, this is currently in radical form, so I want to rewrite this in fractional form, a fractional exponent form, sorry. So because the index of my root is 6, that 6 is going to become the bottom part of a fraction. So this is going to become x to the 1/6 power. Again, the number on the bottom here matches the index of the root. And this is x to the first. That's how I knew there was a 1 on top here. So that's x to the 1/6 power. How about the fourth root of 11 to the third power? How am I going to write that in exponential form? Well, I have a fourth root here, so that means I'm going to have 11 to a fractional exponent, and I know the 4 is going to be on the bottom of that fraction because the index here goes to the number on the bottom here. And because I have, sorry, I don't know what's going on there. Because I have a 3 in here as an exponent on the 11, that's going to go up here to the top. So I can write the fourth root of 11 to the third power as 11 to the 3/4 power. Now, what if I wanted to go the opposite direction? If I started with a fractional exponent and I wanted to go to a root? Well, 121 to the 1/2 power. I want to write this as a root. Well, the number on the bottom here, that's going to go in my index of the root. So I'm going to have the second root of 121 to the first power. So this is, because I have an index of 2, this is the square root. The square root of 121, if you remember from a long time ago, that's just 11. All right, how about b to the 2/3 power? To write this in radical form, the number on the bottom will create the index of my radical, so I'm going to have a cube root. The 2 on top goes to the inside of the radical with the b. So this becomes a cube root of b squared. If we wanted to, we could also write this as the cube root of b, that whole thing squared if we wanted to. These two things are equivalent. You can choose which way to write them. Doesn't matter to me which form these are in. Finally, x to the 7/8 power. Again, the number on the bottom, that 8, will create the index of the radical. This will be an 8th root. And the 7 is going to go into the radical as an exponent with the x. So this is the 8th root of x to the 7th. All right, those are our exponent rules. Hopefully this will help you on your homework 11 warm-up. Again, this is going to be an extra credit assignment. And let me know if you have any questions as you work on this. Thanks so much for your time, and I hope you have a good day.